In this video, we are going to be looking at two problems that show us a graph. And so we're going to want to make sure that we know the key characteristics of the graph that will tell us whether or not it is linear or exponential, and then also how to use that graph to find the equation. So when I look at the graph, I see a straight line. And so I feel like the easy decision here is that it is indeed linear because of that straight line. So that one is very easy to tell. Next thing is tells me to write the equation. So it says when you started your shift, the patient had already received 625 milliliters of IV fluid. The graph shows the total IV fluid infused during the first 5 hours of your shift. Model the amount of IV fluid received. So when I look at the graph, when I look at the 0, this number here that matched up with time is 0 is the start. So I have that piece of information given to me because they gave me a graph that showed me 0. Now, if the graph did not show me 0, then I would have to do more work, but this one does. Next off, in my linear model, the equation that we always base everything on is y equals mx plus b. So in this model, I know b, because that's the start, but I need to know the rate of change. And the rate of change, we said, is slope. So slope can be found whenever you have points, and we had talked about that the formula for slope is y2 minus y1 divided by x2 minus x1. So what I'm going to do is I'm going to look at my graph for some ordered pairs. So this ordered pair right here would be 0 for the x, 625 for the y. And then the next ordered pair that I'm given point values for is time is 1, so that's x is 1. And the output, the y value, is 688.5. So I'm going to use those as my y1, y2, x1, x2. So I always start with my second ordered pair. So in this case, 688.5 minus the 625. And then going the same direction with the x values, so 1 minus 0. So I get 63.5 over 1, which literally simplifies to 63.5. So this is the slope. This is a change of 63.5 milliliters over the course of an hour. And it's a constant rate of change, and I can take my calculator and double check it. So if I add 63.5 on my calculator, so taking 688.5 plus 63.5, I do get 752. So that checks that is the same rate. And anytime you have a straight line, it will automatically be the same rate. So even though I checked it, I really don't have to because I can visually see the line is straight. So now I want to plug these values into my equation to finish out my model. So I get y equals 63.5 x plus 625. And so this gives me a formula. It shows me where to start my line, shows me how fast my line needs to go up to match the image that was given. So taking a look at a second graph. For this graph, I immediately see that the graph is that of a curve. And as we said in our beginning problems, when we see the curve on the graph, that is indication that it is exponential. So that makes the decision with a graph to be pretty straightforward. So this is exponential. It says the client has just taken erythromycin. Boy, that's hard to spit out. The client's body will metabolize the erythromycin according to the graph. Model the milligrams remaining in the client. So again, when I look at my graph, I notice that I have a time is 0 here, and that is really helpful so that I know this 800 is my start. Now, because it is exponential, instead of discussing slope, we need to find percent because exponentials work with percent. So I need to do percent change. And so to calculate percent change, I start with a new minus old divided by old, and that will give me the decimal. And I want it as a decimal, so I don't want to multiply by 100. So this 800 is my old value. My new value 1 hour later is 504. So I will take 504 minus 800 and divide by 800. And so doing the math on my calculator, 504 minus 800 gives me a negative 296. And then I divide that by 800. And that gives me a negative 0.37. So that is the decimal for the percent. So I noticed my start. I have the percent of change as a decimal. I'm ready to use my formula. So my formula y equals p 1 plus r to the t power. And I just need to plug in the appropriate pieces. So I have y equals 800, replacing the p with the 800. I have 1 plus a negative 0.37, replacing the r with that negative decimal to the t power. So the one step that I want to do yet is actually do the math inside the parenthesis there. And so that gives me a cleaned up formula that says y equals 800 parenthesis 0.63 to the t power. And that is the exponential model for this graph. So again, when we're looking at graphs, the key thing is whether or not it's a straight line. If it's a straight line, it's linear. If it's a curve, it's going to be exponential. There are other curves out there, but we're not studying them this week. So your only two choices here are that it's exponential or that it is indeed linear.